Welcome to Codan Radio Communications. This video is part of a series on radio fundamentals and introduces the HF or high-frequency radio technology. We are surrounded by all sorts of invisible particles and waves, some of which are charged, and these moving charges result in electric and magnetic fields. When electric and magnetic fields couple with each other at a right angle, it results in the formation of electromagnetic waves. These waves travel in a direction which is perpendicular to both the fields. They travel through space at the speed of light, and just like light, electromagnetic waves can travel through a vacuum as well. Electromagnetic waves come in varying forms of frequency and amplitude. Even heat and light are forms of electromagnetic waves. Radio waves are part of the electromagnetic spectrum. The radio wave spectrum has a large range of radio waves, from maritime navigation signals used by ships, which are very low frequency, or VLF, to satellite signals, which are extremely high frequency, or EHF. In this presentation, we are going to focus on the HF, or high-frequency radio waves, and how they are used in communications. The range of HF radio waves is between 3 to 30 MHz, according to the electromagnetic spectrum. The typical range of modern HF radios is 1.6 to 30 MHz. So how did we know about electromagnetic waves and radio waves? It all started with James Clerk Maxwell's treatise on electricity and magnetism in 1873. The first radio waves were detected 15 years later by Heinrich Rudolf Hertz, whose practical experiments supported Maxwell's theories. Heinrich's work inspired Guglielmo Marconi's early experiments with wireless telegraphy, using Morse code. In 1901, Marconi successfully demonstrated wireless communication from Cornwall, England, to Newfoundland, Canada, a distance of 3,000 kilometers. So the radio waves that Marconi used were the high-frequency, or the HF radio waves. How does HF radio technology work? A transmitting antenna, shown as TX, emits the HF radio waves, and a receiving antenna, shown as RX, receives these radio waves. There are three types of HF radio waves. Ground wave, which is good for short-distance communication at less than 20 kilometers. It follows the curvature of the Earth and is therefore attenuated. Direct wave, which can be used for long-distance communication between ground stations and aircraft. And finally, sky wave, which uses the ionosphere to refract the signal back to Earth at varying angles, providing long-distance communications. As you can see, skywave covers the maximum distance. We are most interested in skywave to propagate signals. A layer in the atmosphere called the ionosphere refract the HF radio waves, making this technology work over long distance. The angle of the antenna is responsible for the coverage area as it aims the radio waves which are bounced off the ionosphere. This also creates a skip zone, where the ground wave ends and the sky wave starts, where the radio waves are not present as they are not refracted into this area. To reduce or overcome a skip zone, the takeoff angle of the antenna is adjusted. By using a higher takeoff angle for the HF signal, the ionosphere is used to refract the signal back to Earth at a shorter distance. All sorts of voice, data, or signals can be sent using these waves. The ionosphere itself is made of several different layers that refract the HF radio waves in different ways. These range from the closest layer that exists in the day, called layer D, to the farthest layer called F2. These different layers behave differently in the way that they refract HF radio waves. The D layer in particular can weaken or attenuate the HF radio waves, as it contains a higher number of charged particles due to the sunlight. The most common layers used for signal propagation are the F1 and F2. These layers change between day and night. A basic rule for HF radio signals is to use higher frequency radio waves during the day, as higher frequency waves will travel further using the ionosphere. The higher the sun, the higher the frequency required. The higher the frequency, the longer the distance the HF radio waves will travel. What are some of the other factors that can affect HF radio waves? Solar flares can alter the refracting property of the ionosphere. 11-year solar cycles can either hinder or improve the HF radio waves. And finally, something man-made, such as power stations, which produce electrical noise, can affect the reception of HF signals. Apart from these factors, communication through HF radio waves depends on a few other things, like location, local radio rules and regulations. planning for the frequency sets to be used. So if you have the right antenna and these factors covered, you are on your way in the world of reliable long-distance HF radio communications. Codan Radio Communications. Be heard. We go where you go to ensure your people will always be heard.